Hey there everyone, welcome to the very first lesson of Mathing with Diiv. So as I mentioned before on my Facebook wall, these are just lessons I've made to basically give people a basic understanding of mathematics, what it actually is, and how, in further videos, how those basic fundamental principles can be used in the real world, and how they are actually being used in the real world as we speak. So before we can get to that, however, we need to do what I call eating your math vegetables, which is basically understanding the basic terms and concepts and symbols you often see in mathematics. And so we'll first talk about propositional logic, which is basically logic in general, and the idea of what a mathematical proof is. And then we'll go on to talk about sets, functions, sequences, and sums. If you haven't heard about these terms before, no worries, it's perfectly fine. That's what these videos are for. So this is my first video. It'll be a little rough around the edges. Eventually I'll get some editing software so I can smoothen out the rough edges. But for now, let's just get started. So the rules of logic, they basically specify the meaning of mathematical statements. Logic is the basis of all mathematical reasoning, right? And thus of all automated reasoning. Your computers, any kind of artificial intelligence villain in a video game, all those are the basis of logic. They have to be. So we should first talk about how we define logic. Like, what does that mean exactly? In math, everything has to have every statement is a concrete true or false statement. There's no ambiguity. That's what allows mathematics to basically build on itself, and that's how we get very complex structures from simple concepts. So we first begin with a term, and so what I'll usually do is I'll give anytime there's a term, which is like a vocab word basically that you should know about. I'll also give some examples of things that abide by that vocab word. So first term is a proposition. So what is a proposition? Well, a proposition is a declarative sentence. What does that mean? What does declarative sentence mean? It's very simple. It means a sentence that declares a fact. It's a declarative sentence, which means a sentence that declares a fact. Declares a fact, right? A sentence that declares a fact that is either true or false. Or false. And this last part's really important, but not both. Otherwise, if something can be both true and false at the same time, then our rules of logic would break down. We'll actually see later, there's ways of doing proofs where you can show that if you assume the opposite of something, you can actually get something that's both true, a statement that's both true and false, a contradiction. And that's how we show that opposite can't happen, which is a way of proving that the initial conclusion is true. But we'll get into that later. Alright, so a proposition is a declarative sentence that is either true or false, but not both. So, what does that mean? What are some examples of propositional sentences? So there's one that's like, Washington, D.C. is the capital of the United States of America. Right? And is this a proposition? Yes, it is. Is it true, or is it? The first thing you ask is this a proposition? Yes, it is, because it declares a fact. Washington, D.C. is the capital of the U.S. Now, the next thing is, yes, now we know it's a proposition. Is this proposition true, or is it false? Well, in this case, it's true. All right. Let's put examples. Now, it's another example. right? So another example of a propositional statement would be something, oh, let's do like a basic mathematical statement that you've seen before, like 1 plus 1 equals 2, right? And that's it. Does it state a fact? Yes, it does. It's stating that 1 plus 1 equals 2, right? Now, is this true or false? Well, in this case, it's true by the way we've defined addition on real numbers. And we'll get into that, what it means to be a real number and all that. But by the way, so in this case, the statement's true because we have definitions for what this plus symbol means, what this 1 means, what this 2 means, and based on the definitions we have for these symbols, this 1 symbol, this plus symbol, and this 2 symbol, this statement is true. And actually, before let's just do one more example, and then I'll try to make a point here. It's important. So 2 plus 2 equals 3. So is this a propositional? Is this a proposition? Yes, it is. Now, because it states, it's a fact. It's saying 2 plus 2 equals 3. Now, is this fact true or false? Well, in this case, it's false because of the way we've defined add, 2, and 3. The symbol 2, the symbol add, and the symbol 3, right? Remember, everything in math is a symbol, and these symbols have meaning because we gave them meaning. These weren't things that were like flying around in the sky or anything like that. These were human constructs, this 3 symbol, this 2 symbol, this plus symbol that we created, and we gave them definition and meaning, and based on that definition and meaning, we know that this statement, 2 plus 2 equals 3, is false. Because it actually, 2 plus 2 equals 4. Alright, so now that you've seen examples of things that are propositional statements, or propositions, what are some examples of things that are not propositions? Let's see. There we go. Things like questions, right? So, things that are not propositions. Not propositions. Proposition. Like, what time is it? What time is it? Is this a proposition? No, because it's a question. It doesn't state a fact. Also, statements that are ambiguous are not propositions, such that like Patriots fans are usually moronic. And by the way, I'm just kidding. I have nothing against Patriots fans. But you can see this is not a mathematical statement because it has this word usually, which is ambiguous. Therefore, it doesn't have like a distinct true or false value. So this is not a proposition. The thing that helps math be correct is the fact that it should be free of ambiguous statements like this. You might see these kind of statements in English, but you won't see this kind of statements in math. And so, or things like, and a similar example is like, read this carefully. So this is not a declarative sentence. Well, for one, it's instructing you to do something. It's not actually stating a fact that's either true or false. Alright, now actually let's look at some math statements that are not propositions. Something like this, actually. So like, x plus 3 equals 4. This is actually not a proposition because it doesn't state a fact that is either true or false because you don't know, there's ambiguity. You don't know what x is. X could be anything. So this is not a proposition. And the same applies to something like x plus y equals z, where x, y, and z are variables. Once again, you cannot determine the trueness or the falseness of this statement because there's ambiguity. You don't know what these variables are representing. Okay? So that's what a proposition is. A declarative sentence, to recap. Proposition is a declarative sentence. And what is a declarative sentence? A sentence that declares a fact that is either true or false, but not both. And by the way, so it's been shown that the average human life attention spans around 10, 15 minutes or something, especially for younger people. So I would recommend that, if you're starting to get bored, there's no point in like drudging through this. You should pause it, go do something else, maybe something more interesting. Go try, go start exercising or go start cooking or whatever, tickles your fancy, and then come back. A big part of learning is knowing when to pace yourself. Kind of stop, allow yourself to kind of digest the amount of information that's already gone in, and then try something else. Or you can pause the video and try some examples on your own. That's a very big thing, and that'll kind of shift the topic and kind of get your like refresher attention span in a sense, and then come back. All right. And sometimes it's cool to also never study the same thing over and over, because you'll get bored of it and you might like dislike it, and then that will, if your attention span starts to go down, your ability to absorb information starts to go down, right? And then you don't get as much out of the lesson as you want. All right, so let's go on. Another term, sure. Okay, proposition. So another term that we'll have is propositional variable. Variable. Okay. So what does that mean? All right. Propositional variable is, as it's stated, it's a variable. Just what is a variable? A variable is something that can take on many different values, like you saw the x, y, and the z. It's just a symbol that can take on many different values. That's a variable, right? So a propositional variable is a variable that represents a proposition. So it's a specific kind of variable, right? That represents proposition. Represents a proposition. So what's an example of this? A variable that represents a proposition. So you could say like, let p, so p is going to be my variable, equals let p equals 1 plus, let p equals 1 plus 1 equals 2. So you can see p represents this proposition, right? And so you can say q, you can make another variable, q equals, it is raining today. It rained today. Right. So that's another. So these are just variables that represent a proposition. Alright? And then the truth value of a proposition is true if it is a true proposition, and the truth value of a proposition is false if it is a false proposition. Right? So now the area of logic deals with propositions is called propositional. Okay, so when you start doing like some kind of algebra math with these, we call that propositional logic. Some people call that Boolean logic, propositional calculus. So what does that mean? That means we can start. It means like, how do we combine these together to make more complex statements? For example, what if we want to say 1 plus 1 equals 2 and it rained today? Or 1 plus 1 equals 2 or it rained today. It's a little weird. So a better example would be 1 plus 1 equals 2 or 2 plus 2 equals 4 or something like that. Or it rained today or it didn't rain today. Oh, that would be interesting. So something is something and its opposite. So remember, if a statement can be true, then you're saying that the opposite, because it's a fact, then that means the not of that statement, also known as the negation of that statement, or the opposite of that statement, has to be false by the rules of logic, right? So what do I mean by that? So let's go over a definition. All right. So let p, the variable, be a proposition. So remember, p is a propositional variable, so now it could stand for some proposition, right? Example. Okay. Let p be a proposition. Okay. So then the negation of p, and if any of you have done like any kind of programming, you've heard of a not operator, it's basically the same thing, right? The negation of p, and so what we do in math is whenever we usually make definitions, sometimes we'll attach symbols to them, right? So in this case, we have a symbol like this, this is what we call the not operator. This is what we call the not or the negation operator. Negation or not operator. The negation of P. Right? The negation, let P be a proposition, then the negation of P we denote. So denote means that this is a symbol we're going to attach to that term. So which we denote as not P. Okay? This will be our not operator that I mentioned before. Is the statement it is not the case that P. So what does that mean? So let's go. For example, if P equals 1 plus 1 equals 2, then we're saying that not of P, or the negation of P, means it is not the case that 1 plus 1 equals 2. So as you can see, this negation operator, takes in, and we'll actually go into what an operator is. It's very similar to a function, but basically an operator is a function. So this negation operator takes in as its argument. So actually, I'll refrain from using those terms for now until we get to functions. But basically, what this negation operator does is that you give it a proposition, and what it does is it basically spits out the opposite of that propositional sentence. So if the proposition was 1 plus 1 equals 2, the negation basically does the opposite of that, which is it is not the case that 1 plus 1 equals 2, right? Which is the opposite statement of 1 plus 1 equals 2. So now, you don't always have to say it is not the case to be. People will say, you can say things like, someone says Michael's PC runs Linux. Then the negation of that would be Michael's PC does not run Linux, right? That would be the opposite statement. So as you can see, this is why it's important for a proposition to be a declarative sentence that is either true or false, but not both. Because that's how you get this. That's why there exists an opposite statement. Because it is either true or false, it has an opposite, which will be the opposite Boolean value. Alright. Alright. So what's cool about this is that now we can do something. So now we have these variables that can either take on the value true, which we'll sometimes say as t, for brevity, or false, right? We have these values that can either be true or false. So what this means is that when we have operators, we can actually define them very, very simply by saying that if we have something p, we can just say, like, here's a variable p, and we can define what does this not of p mean. Well, we said that p has to be a proposition, so it can take on the value true, or it can take on the value false. And so if it takes on the value true, then the not of p is going to be false. And if it takes on the value false, then the not of p, or the negation of p, is going to be true. So this is what we call a truth table, right? So every time mathematicians are making these new Boolean or operators or propositional like operators, like this negation symbol you see here, they have to define it rigorously to say what it exactly means. They define it by showing this truth table of what it does. If you have a proposition, which is a variable, that either takes the values true or false, when you apply this operator to that proposition, you get out a new Boolean value as defined by the truth table. This is basically saying what we logically understand as, like, oh, it's the opposite statement. Okay. The value takes on. So one more. So this was like our not. So then, of course, you have things like 1 plus 1 equals 2, and it did rain today, right? And that's what we call the conjunction operator, or the conjunction. And so we usually use the symbol of this, the conjunction. So you can think of this as an and statement in English, right? You can think of this as a not statement in English, this negation operator. you can think of this upwards mountain-looking symbol, just basically like a triangle without the bottom. This upward symbol as what we call a conjunction operator, or an AND. This is like an AND. Previous negation operator was a NOT. So this allows you to make statements like when we had 1 plus 1 equals 2 and it rained today, we can do something like P and Q. The important thing to realize is that this whole thing is another proposition, right? And we sometimes call these compound propositions because you took some basic individual propositions and you made a whole new proposition using those single propositions. So we call them compound propositions. So now these terms aren't super important. It's more you understand the concept behind them, right? So now let's to make this clear, let's do a truth table. So you have a P, you have this propositional variable P that can take on the value true or false. And you have this value Q that can also take on the symbol true or false. But there's something important to be here. So you can see that there's two choices here. Two choices. Right? True or false. And then there's two choices here, right? Two choices. So what this means is that you can first get something that's the P. So you have two choices for P and then you have two choices for Q. So that means there's a total of like 4 different combinations, right? Because you pick one of these guys, then he gets 2 options. Then you pick his other value, then there's still 2 more options. If you count all those different options, you have 4 different options, right? You have true, true, they can both be true. P can be true, Q can be false. P can be false, Q can be true, or they could both be false, right? So that means if we're doing a truth table to define it here, like we did for the negation operator, we're going to actually need 4 rows instead of 2. So we get true, 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 false, false, true, and then false, false, right? Okay. So let's do this. Okay. So now what are we going to do? We're going to, alright, so yes, so we're going to now define this then. So now we have to, but one thing that's important to know is that there's only 4 different combinations. You see that, right? And that's important because what that means is our truth table has to be exhaustive. It has to cover all possible cases. Otherwise, this AND operator becomes what we call ambiguous, right? You can't have an operator or a new symbol you define be ambiguous because in math it has to have a definite meaning. So once we tell what values happen, so if P is true and Q is true, you define the conjunction operator or AND operator to be true in this case. In fact, the conjunction operator is only true, this compound proposition that is only true if both of its individual statements are true, right? So in this case, where P is true, Q is false, this is false. The overall compound proposition is false because one of those things are false. In the case of P being false, Q being true, it's the same situation. It's going to be false. Now in the case of P being false, Q being false, this whole thing is false. Now, only as long as one of them is false, the whole statement is false, right? So since they're both false, it's still going to be false. So as you can see, the conjunction operator is only true, or this AND operator, AND is only true if they both hold true. That's what you know, right? This and that, right? When someone says, well, it's raining today, and I went out with your girlfriend. That'd be terrible. But as you can see, the AND operator implies that both of those statements are being true. If either one of those was a lie, that entire statement, that entire AND statement would be a lie. Okay, the AND operator. Conjunction AND. And then the final one is, of course, the what they call the disjunction operator, or I like to say as the OR operator. It's just like the upside down version of this operator. Disjunction. The OR operator. And so the truth table for this is very simple. This symbol says that the overall statement P or Q, this statement here is true as long as at least one of these guys is true, right? As long as at least one of these guys, that's the way we've defined it. So an OR statement is true as long as one of these guys is true. So to be more specific, this is more what we call an inclusive OR, and I'll explain that in a second. P or Q. So it's like, I want you to go to the zoo if the zebras are out today, or the monkeys are eating their bananas. So in this case, as long as one of those ends up being true, then you're going to go to the zoo. It's very simple. So let's go over that. So if P was true, Q is true, then it's an OR operator, so it's going to be true, right? Now if P was true, but Q was false, well, only one of them needs to be true, so this is going to be true. If P was false and Q was true, well, only one of them needs to be true, so this is true. Now, if they're both false, however, well, then that's going to be false, because you need at least one of them to be true, and in this case, neither one is true. So now, you've got this conjunction or operator, and you've well defined it. So now we've got and. So to recap, we now have like a not, which is like the opposite statement. We have and then we have or. And if you think about it, this is all you really need, right? Because if you have statements that are either true or false, you can now start combining them to make more complex statements by using ands, ors, and nots, like you do in English. Very cool. This is actually alright. So actually, there's one more operator I'd like to show you, and it's actually, you'll see later that it can actually be made using a combination of these ones. These, if you have and or not, you can basically construct any other kind of more complex operator. These are your bases. These are your base operators. What I mean is the notion of an exclusive. As you can see, this is an inclusive OR. What do I mean by that? It means that as long as one of these is true, this is true. So this thing where they're both true, that is still a true statement. But sometimes you have something called an exclusive OR, where only exactly one of them can be true, but not both of them, right? So like, I want you to go to the zoo if the elephants are out today, or the monkeys are eating bananas, but not both. That's what an exclusive OR is. And a lot of the times when it's a car dealership and they tell you can choose this or that, that OR is usually an exclusive OR, right? You don't say like, oh, well, you didn't specify, so I get to have both of them, right? No, they'll probably stop you if you try that. So, yeah. So sometimes being smartass doesn't always pay off. But it's good to know. So that's what we call an exclusive OR. And in computer science, it has a lot of meaning, especially in computer science. They'll sometimes use a symbol like XOR to mean exclusive OR. So let's actually do the... I'm not sure if there's a formal operator here, but let's just call it XOR. So say you had a propositional P, Q, let's actually XOR. And in fact, before you go on, I'd like you to pause this video and see if you can. So the definition of an XOR is that either of the statements should be true, but not both. And exactly one of the statements should be true, but not both. So can you try to come up with the different truth table combinations for this? I recommend that you pause the video now and try it yourself. Alright, so yeah, I'd recommend you pause the video and try it for yourself. Okay, I'm going to assume you pause the video and try it for yourself, because a lot of, in mathematics, practice does make perfect. A lot of this, you have to play around with it, get a feel. The only way to truly understand whenever you're exposed to new symbols or new concepts, you have to play with them. You gotta mess with them. You gotta roll in the hay with them and get intimate with them if you really want to understand what they mean, right? I mean, the same goes with the person. You can't, if you don't get to know a person, you can't really interact with them at the deepest level. And the same applies with mathematics. So in this case, the true and the true is actually going to be false, because by our rules, only exactly one of them has to be true, not both. This one, you have P is true, Q is false. Well, then yes, that's true, because exactly one of them was true and the other one is false. Same applies here, where Q is true, but P is false. Now in this case, they're both false. That's still false, because you need exactly one of them to be true, and neither zero of them are true. So it's false. So that's the X. So the biggest difference between the OR and the XOR actually is in the first case where they're both true. In the inclusive OR, that's still a true statement, but in the exclusive OR, that's a false statement. Alright. So, I guess now would be a good time to just kind of take a break. This is a pretty basic concept, but it's to show you that actually math is based off of very basic logic. I know you might say, well, I don't see any numbers. Are you sure this is math? This is actually very much math. In fact, this is the foundation of math. And yeah, so I would take a break, and if not, I can give you a little history lesson, I suppose. That can be kind of dry, which is why you can just skip right through this. And so I'll have a big, alright, this history lesson is done kind of thing at the end once I'm done with this history lesson. But there's this guy called George Boole, and he's known to be the father of Boolean logic. What is Boolean logic? This is that true and false propositional logic that we just went over. Right? He was the son of a cobbler, and he was an English guy. And, well, see, he didn't like the way math books were written back in the 1800s, so he wanted it to be more rigorous, more concrete, less ambiguous, so kids could really grasp what math is. And so he actually read a lot of works of really great mathematicians, like Lagrange, and you'll hear more about Lagrange as I go into other things. And he made this book in 1848 called The Mathematical Analysis of Logic, where he formalized these notions that we talk about. Now you might say, well, this is so basic. Well, it's actually really important to formalize these basic notions, because when you start getting the more complicated notions, the only way to determine the truthiness, as Colbert would say, of those more complicated statements is by breaking them down back into these simple statements and understanding the flow of logic that goes in those statements to figure out if that statement is either true or false. Alright, so yeah, so let's get back to the idea of let's get back to the idea let's get back to propositions, and we're going to do our final operator or construct in propositions. And this is probably I wouldn't say the most important, since you need the ors and the ands, but this is like the final thing that allows us to actually do math. Once we have this last thing, we basically can do math, which is kind of cool. Actually, this is like the last building block. So this is what we call a conditional statement. Alright, so term conditional statement. Okay, what does it mean? Conditional statement? Well, so I'm going to define it in a kind of a formally kind of way to get you used to how you'll see like when math books start to talk about math. So we'll say, let P and Q be propositions. Right? So what that means is P and Q are these variables that represent propositions, or propositional variables, like we talked about in the last section. Let P and Q be propositions. The conditional statement, and I don't know why I'm doing a high-pitched voice, since none of my professors ever had high-pitched voices, but the conditional statement, and so now we're going to make this new symbol, conditional statement, P implies Q is the proposition so you can call this arrow thing an implication statement if you want. I don't know if that's a formal term, that's how I like to it. Is the proposition, so if P then Q. The important thing to see here is that this arrow operator, or this implication operator, it takes in two propositional statements, one on the left side, one on the right side. This is the format of how we write the symbol, where we put one of the variables on the left of it and one of the variables on the right. And what it means it means if P, then Q. Right? And so what is that? So now we need to have like that truth table of it, right? So first they're going to tell us what it means in English, and then we can construct the truth table. That's how definitions work. The definition has to come to us in English, and then we can put down like a definitive. So the conditional statement, and I'm kind of writing it out so I go slower so you have time to kind of process. The conditional statement, P implies Q, is false when P is true and Q is false. Okay? And true otherwise. Alright, so actually a good exercise right now would be for you to come up with the truth table for this, right? Because this is an operator that takes in propositional variables and it outputs a propositional. It takes in propositions and it outputs a proposition. So, therefore, you can construct a truth table on it. Okay? But before I let you do that, let's just say, so what we usually say when we have something like P implies Q, we call P, and we probably got this from science, we call P the hypothesis, and Q the conclusion. Or I guess since math and logic is the basis of everything, maybe they got it from us. Ooh. But anyway, so we call P the hypothesis and we call Q the conclusion, right? Because you're saying if this, you're making your hypothesis, then Q, then that's the conclusion that results because of the P, right? The P causes the Q in a sense. That's the way you can kind of think about it. The P causes the Q, right? So first just try to come up with the truth table for this. So you should pause the video and try it out yourself. P and Q. And so as you know, P can take on two values, Q can take on two values, so it's going to be four different combinations, and now they each need for this statement, for this arrow operator to be well defined, right? Well defined means it's not ambiguous. It has a clear meaning. We need to fill out the true and false values for each of these. So pause the video and do that. Okay, I'm going to assume you paused the video just now and you did it yourself, so let's try it. So let's look at this thing. Alright, condition statement, P implies Q is false when P is true, and Q is false. Okay, it's false when, let's get that one done first. It's false when P is true, so I look at all the different ones, there's two cases where P is true, and Q is false. So P is true and Q is true, I don't care about that one. In fact, you're using a conjunction logic right here actually, right? You're doing it right now. P is true, and Q is false. There we go. Alright. And then P is true, Q is false, and then this whole statement is false. That's by definition from that English definition. We got concrete meaning, and it says, and true otherwise. Otherwise means every other case that's not this one, right? So this is true. So if P is true, Q is true, that's true. P is false, Q is true, that's true. If P is false, Q is false, that's true. So before we go on, whenever you do these definitions, you've done the exercise, it's always going to stop, because everything in math kind of has this like deeper philosophical meaning or conceptual understanding. And so if you just keep going through the symbols without actually stopping, like, wait, what is this symbol? What is this operation? What does it mean? Right? Then you'll kind of get lost later on. It's important to understand what it's saying, right? So 1, 2. So a useful way. So I'm going to there's this book called Rosin, which basically is a really good discrete math book. And I'm just going to kind of just quote them exactly here. So a useful way to understand the truth value of this conditional statement, this P implies Q statement, is to think of an obligation or a contract. For example, the pledge many politicians make when running for office is, if I am elected, then I will lower taxes. You know, the whole Grover Norquist thing, right? So if the politician is elected, voters would expect this politician to lower taxes. Furthermore, if the politician is not elected, then the voters will not have any expectation that this person will lower taxes, although the person may have sufficient influence to cause those in power to lower taxes. So what they're saying, okay, this is actually a really good example. So let's look at that statement, alright? If I am elected, then I will lower taxes. And I will lower taxes. So remember, this implication statement, this if-then statement, or if this can be written mathematically, right? So the P will be, I am elected. Right? This is a statement that is either true or false. And then the other proposition that statement that is true is I will lower taxes. Right? I will lower taxes. And then note that if you do P implies Q, you get the sentence above. If I am elected, then I will lower taxes, right? Sentence above. Sentence above. All right. So this is important. So now, if he is elected, right, the thing is true, then we expect him to lower taxes, like he said. That's why this whole statement becomes true, because he lives by his thing. But if he's elected and he doesn't do it, if I'm elected now and he doesn't do it, we consider that statement to be false. It's like, what the heck? That's how we define it, right? It's like, that's super weird. You just said if you're elected, you lower taxes. I expected that causality to happen, right? The cause and the effect. So if I am elected, then I will lower taxes. So then that should be, so if you're elected, then I expect those taxes to be lowered. That's the causality. So this implication is like a causality statement. So what happens is if he gets elected and he doesn't lower the taxes, that's why we consider that statement to be false. That's like, what the hell? That's why that statement's false, right? So if the hypothesis, so remember P was called the hypothesis, the thing on the if statement is the hypothesis. If that is true, then then we expect the Q to be true, which is why the whole statement takes a truth value. And if it's not, then that whole statement is false. Now the more interesting thing is that, let's say I wasn't elected, right? Now why is this whole statement true then? Well, it's very simple. So you can think of it as if that person didn't get elected, then that whole causality isn't there because the cause didn't happen. But that just because the cause didn't happen doesn't mean that affects the effect. For example, someone else who got elected could lower taxes, right? Or taxes may never get lowered at all. Like anything can happen to the effect. The effect, there's no force happening, right? In other case, like this cause and effect, the cause is the force that makes the effect happen, right? But now if the cause doesn't happen, then then that effect, it could happen by another thing could cause it, or it may never happen at all, right? So therefore, that's why these two statements are true, because since the hypothesis was false to begin with, we just don't know what to say about, like, it doesn't really affect the Q in any way, so we say the overall statement is true, because it could still, Alright, so another example would be, if I get 100% on the final, then you will get an A. So, that, like, if you get 100% on the final, then if your teacher told you that if you get 100% on the final, then you'll get an A, and you get 100, you better freaking expect an A. That's what you want that statement to be true, right? That Q, the Q statement, which is you'll get an A in the class, that should be true. And if it's not, then you'll get pissed off, hence why that overall P implies Q statement is false. But now if you don't get 100% on the final, that doesn't affect whether or not you'll get an A. Maybe you got a 99 on the final, and that was still good enough for you to get an A. Or maybe you got a 0 on the final, and then you didn't get an A, right? So you have no idea. It doesn't matter what that effect, you have no idea of the effect. It's the hypothesis itself as well. Okay? So that's the implication statement. Or the conditional statement, right? Or the conditional statement, yeah. In case there are the conditional statement. Alright. Okay, so this is really important. So now that we know what a conditional statement is, we should go over something what we call the some other like derivations or variations of a conditional statement. So this is like P implies Q. If you have a statement P implies Q, this is a conditional statement, right? This is a conditional statement. P implies Q, it's a conditional statement. So we're going to go over some new terms. Conditional statement. Okay. So the converse. So here's a new word, converse. We define this word converse. The converse of this conditional statement P implies Q is Q implies P. Right? Converse of P implies Q is Q implies P. The contrapositive of P implies Q is not Q implies not P. Okay? And then finally, the inverse. So now you don't have to memorize so much vocab, but it's just good to let's just have it around so you understand. As you work with it, you won't actually be memorizing these things. You'll just kind of understand them. So the inverse of P implies Q, because you'll be working with them so much that they just become, is not P implies not Q. Okay. And now here's a really good exercise. So what I want you to do is, I'm going to put the truth table here again, just, repetition. I'm going to put the truth table here if P implies Q, and what I want you to do is I want you to actually do the truth table for the other ones. So let me just get that set up here. True, false, false. Alright. True, false, true, yep. Alright, so you should try now I'd like you to try the, try it now for converse, so try Q implies P. Alright, and then I want you to try it for true, false, and leave comments if you want me to have at least pre-written, and I'll put when I have time, I'll actually put up on the website some LaTeX document. That's basically a nicely formatted document that has this all typed up clearly, because my handwriting might be a little bad. So I want you to fill out, this one was called this was the converse. Then we have the contrapositive, which is not Q implies not P. Q. Now I'm actually not going to go through the lines anymore, just to speed up a bit. PQ, and then not P implies not Q. So yeah, take a second to fill out the true and false values for all these guys, okay? And yeah, so you should pause the video and do that, okay? So go and do that, alright? Alright. Okay. So let's go. So what was this guy? This guy was the converse. Okay. So now the converse is we flip the P's and the Q's, right? So what's going to happen now is, alright, if this is Q is true and then the P is false, then this is going to be false, right? And then, because we basically just flipped the P's and the Q's, in this case it had to be this guy was false, so we just flipped them around, so that's like this guy. And then the rest of them are now going to be true, otherwise, by just going by that definition, right? Okay. So something that's important to note here is that just because an implication is true, if P implies Q is true, like it is here and here, right? Oh, sorry about that. Let's actually just finish this up first. So yeah, I actually wanted to let you finish this up. So let's go through all these really quick. Okay. So not P, not Q. Let's do this. Okay. So now in this case, not Q, not P. So not Q is going to be So in this case, first let me get the one, so it's the equivalent of the conditional one is you just want to find that true-false one. So in this case, where is this guy going to be true? This guy's going to be true wherever these guys are false. So these two guys, right? And then when this guy's false, so this one that's true, alright? And then I look at these guys, so it's the not of P, so then this would be true, false. So this guy's going to be false, and then the rest of them are going to be true. Yes, so what was this one called? This one was called the contraposition, right? So I'm going to put that contraposition. And here's something that's really cool. Look at the truth tables of the original P implies Q and the not Q and the not P. They are logically, well, this is what we call logically equivalent, as in they have the same truth table. For the same values of P and Q, they output the same Boolean value, right? If you have a true, true here and a true, true here, they're both going to output true. If you have a true, false here and a true, false here, these two statements are exactly the same. So what that means is that a conditional statement and his contraposition are exactly the same. This is not true, however, for the converse, because as you can see, their truth tables are different. And as we'll see here, it's also not true for the inverse. This is the inverse. Inverse, converse. And this is the original implication. Oops, I think they changed the color accidentally. Original implication. Alright. So now let's go over this. So true, 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 false, true, true. Alright, so P, not P. So then these guys, not Q. So this is going to be true, false, I believe. Now you should check me on this. I could be wrong, so you should actually, and if I am, you should send in the comments. So now watch. So P, now this P is false here. Not P is going to be true. This Q is true, so not Q is going to be false. So we get a true-false thing going on. We get a true implies false thing, which we know is false, and everything else is true. Now what's interesting here is that the converse and the inverse are actually logically equivalent. Yep. So that's kind of cool. So you can see the converse and the inverse have the same truth value, so they're actually logically equivalent. They're the same thing. So the converse statement and the inverse statement are actually the same thing. So now you might say like, oh, well, this is really abstract. True and false. Yeah, let's actually do some sentences and see that, all right? Okay. So let's do, so let's look at the statement. The home team wins whenever it is raining. It is raining. So this is important. So sometimes math statements won't be like in an if-then kind of thing. That's really convenient. Sometimes they'll be written in other ways, like so you'll have something like if P then Q. That's, you know, that one. If P, and they'll put a comma, and then they'll say the Q statement, right? Or they'll say something like P is sufficient for Q. That means the same as the if P then Q. Or they'll say something like Q if P. Or they'll say Q when P, right? Or Q whenever P. Or they'll say a necessary condition for P is Q. Or they'll say Q unless not P. So usually they won't be that encrypted. They'll try to be very, like, it depends on the math person you're talking to and like the language they use, but these all mean the same thing. P implies Q, P only if Q. A sufficient condition for Q is P. Q whenever P, Q is necessary for P, Q follows from P. I'll put this in the, when I write up the doc, I'll put all these different conditions, and they all mean the same thing as P implies Q. So now, based on that, let's go back to this sentence. The home team wins whenever it is raining. So this is actually a P implies Q thing, right? In this case, P equals it is raining. And actually, you should be doing this yourself, darn it. So you should pause the video. And so even if I don't tell you, it's always good for you to pause the video and try it yourself, right? Because you have the knowledge to do it. So you should. Raining, the home team wins. Home team wins. home team wins. These are obviously propositional statements because they can be either true or false. Team wins. Okay. It is raining. The home team wins. Got it? Alright, so let's do this. P implies Q. So yeah, so what this is saying is like if it is raining, then the home team wins, right? That's what it's saying in the sense. The home team wins whenever it is raining, right? So now what I want you to do, so yeah, so the first one, P implies Q. If it is raining, then the home team wins. It's the same sentence as that whenever one. The home team wins. Now if you think I should pre-write or pre-type these because it's going too slow for you, let me know, but I think by going this way I'm going at your pace, and of course if you're getting bored you should pause, go on, and you can always play this video at a faster speed or whatever. If it is raining, then the home team wins. Alright, good. And then that's the P implies Q. Now I want you to pause this video and try to write the contrapositive statement of it, the converse statement, and the inverse statement. Can you do that for me? Alright, pause the video. Alright, I'm going to assume you pause the statement, so that's good. Let's begin. Alright, so the contrapositive is the not Q, right? Not Q implies not P by definition of contrapositive, as we defined above. So what that means? That means if the home team doesn't win, then it isn't raining. You can see why these two statements are logically equivalent. They have the same truth value because we said right here, if it is raining, so let's say that's true, it's raining, then the home team wins. So if you're assuming this entire implication is true, if this whole thing is true, this if P then Q, if that's a true value, right? So if this P implies Q right here is true, there's only, right? This P implies Q statement is true, they can only take two possibilities, either the true or the true false, but they already told you that this P1, now if we say that if it's raining, now this has a value, it's true. Now it can't be this combination anymore, so you're left with this one, this whole row right here, right? And that's how you know that the Q statement's true. See how that works now? So if it is raining, then the home team wins. So now if it's raining, so the home team wins. So now the opposite of that is the opposite statement of that, which is this one, is now we flip it around. So we flip the not of the conclusion. So if the home team doesn't win, that's the opposite of the home team wins, then it isn't raining, right? That makes sense because we know that if it rained, then the home team's gonna win. You're guaranteed. That's what that first statement is saying, right? So the opposite statement is saying, well, if the home team didn't win, then you know for a fact it didn't rain because you know if it rains, they win. Therefore, since they didn't win, now you know they didn't win, it couldn't have rained because that would contradict the previous statement. So, ta-da! Alright, so that's cool. So now let's try the converse. Q. So the converse is the Q implies P, right? Yep. So at least if you ever forget, just go back, check back your definitions. Q implies P. So that one is going to be with the Q statement, if the home team wins, then it is raining. This is a perfect example. Okay, so as you can see, this is a perfect example that P implies Q does not mean that Q implies P. Why? Look at this. If the home team wins, then it is raining. That's not necessarily true because if the home team could win, right? They could win. Let me rephrase that. So you know that if it is raining, then the home team wins. So that's the causality. It rains, that causes the home team to win, right? But that doesn't mean the opposite is true. Just because it rains, the home team wins, doesn't mean that if the home team wins, that causes the rain. Like it doesn't work that way. If P implies Q is true, that doesn't necessarily, it could be, but it doesn't necessarily guarantee that Q implies P. That's why they're not. And you saw this. That's why these truth tables are not exactly the same. That's why P implies Q's truth table was not, because that's not always the case. So if the home team, because they could have still won, right? But then just whether or not they win or lose doesn't cause the rain to happen. But what this statement is saying is like whether or not it rains. If it rains, the statement is saying if it rains, that will cause the team to win. All right. So next, but now let's do the contrapositive, which is the not P implies, or I'm sorry, we just did the inverse, which is the not P implies not Q, so not P implies not Q. Okay, so this means if it doesn't rain, then the home team does not win. Does not win. Okay, this is a really good example of something. So as you can see, so now it doesn't rain, right? Does that cause the home team to not win? No. So this is really important, right? So all we have here, this P implies Q, all it does is that if it rains, it causes the home team to win. So any other combination is not guaranteed. That combination is guaranteed. So the contraposition one, in the contraposition case, if the home team doesn't win, then you know that causality is true. That opposite one, because they have the same truth table. If the home team doesn't win, then it isn't raining, because you know that rain causes them to win. So that gives you information. So you know that information is true. Therefore, if they didn't win, it couldn't have rained, because we know that rain causes them to win. But that doesn't mean, in the case of not P implies, if it doesn't rain, then the home team does not win. If it doesn't rain, that says nothing about, like, if the hypothesis is false, that says nothing about, like, the conclusion, right? They could still win, right? The other one causes them to win, but if there's nothing causing them, but if it doesn't rain, this doesn't cause them not to win, right? They can still win. Or they may lose. They can still win or lose, but you don't know anything about that. So that's the important. And you can see that logically because their truth tables are not the same. Alright. So, if you're a little confused by that, I'll have some resources and we'll have some more exercises, but hopefully you kind of get the idea. Maybe pause and think about it for a second. And so mathematically, though, the truth tables not being equivalent is the thing showing you that the two statements are not the same, right? Because they don't have the same truth table for the same input values. They don't have the same output, right? So you can think about these. We'll go over functions in a second, but like two operators or functions, like these two symbols, they're only equal if their input-output pairs are exactly equal, right? And they're the same one, and they're the same thing. So that's what we say. We say two statements are logically equivalent if they're two compound propositions have the same truth value. We call them logically equivalent. Right? Okay, so one final one is we're going to talk about what we call the biconditional operator. So biconditional operator. This is like that double arrow going both ways. What this means is that P implies Q and Q implies P. Alright, so this one's true, this one's true. Right? This is really cool. What this means is that the statement P implies Q is true, and its converse is also true. So this is a really cool one. This one does say that if P then Q, but it also says if Q then P. So they both cause each other. They both if the first one's true, it causes the next one to be true, and then if that other one is true, it then causes the. So in general, that's not true. But if someone tells you this, that it's biconditional, this is where you'll see in math. You may have heard in the geometry class or some other class, IFF, if and only if. So when you see that symbol IFF, it just means if and only if. So that means the same as this biconditional operator. It means that it works both ways, right? If P then Q, if Q then P. So let me give you, so remember, new operator, new truth table. So the biconditional operator is true if, so like, let me just give it to you and let me show you. So true, false, false, true, false, false. So what this means, the biconditional operator is true when they both have the same truth value. When the P and the Q have the same truth value, then this statement ends up being true. If they have different values, it's different. Now that's weird, because I told you, when I told it to you, I didn't define it this way. I said like, oh, it means that this one is true and that one is true, right? And right here, the P implies Q is true and the Q. So to see that, what you should do actually is you should try P implies, so you should write it. So this is really cool. So make a table where you do P, Q, P implies Q, do a Q implies P, and then do a P double implies Q. And so I want you, so for the different values, I'd like you to pause it now and try it for yourself. So do a true. Now, for some of you thinking this is really basic, it's because I won't go over this again. And as you go into real math statements, this is, I'm assuming you've understood logic, right? That's right. This is literally our last thing in logic. And yeah. So this is, once we have this, I can actually go into things like proofs and stuff like that. So I just want you to be able to do that. Alright, so let's try this. Alright. I think I've beaten this to death, but like, alright. P implies Q. So remember, the P implies Q thing, when this guy's true, then the next guy has to be true. Otherwise, the overall statement's false. So if the P is true, then the Q has to be true. If the Q is false, then this whole thing is false. That's what we put. Otherwise, but if the P is false, we know nothing about. Nothing's causing, like nothing's affecting Q, so either statement could be true, we don't know. The Q could either be false or the Q could either be true, we don't know. And then the opposite case, you look at where the Q is true and the P is false. So that means since Q is true but P is false, that shouldn't happen. It's false, and then it's true in every other case. Okay. Now P implies Q as shown in the logic table above. True, true makes true. True, false makes false. False, true makes false. And then false, false makes true. Okay, here's something that's really cool. Alright. You see what happened here? You see this? So like, remember the AND operator? Now if you did an AND, I'd like you to do, now if you look at P implies Q and Q implies P, you look at this AND guy right here. So if this guy is true and this guy is true, then this AND sorry. Give me a second. Q implies Q, Q implies P. Alright, so if this P implies Q is true and this Q implies P is true, then we know the way AND works, this whole thing is true, right? If this guy is, if P implies Q is false and Q implies P is false, false, false makes false, right? And P implies Q is false. Yeah. Give me a second. True, false. I'm sorry, let me just reorganize this. True, false. True, true. So this is an AND statement, so this is going to be true. True, false. So one of these is false, so the AND is going to be false. One of these is false, so the AND is going to be false. In this case, they're both false, the AND is going to be false, right? You see that? True, false, false. Okay. So right? So what happens is that in the case of true, if you go back up here, I want to show you that these things are logic. So you can see that the AND of these guys, this P implies Q and Q implies Q, will give you actually the same truth values, right? True and true makes true, true and true makes true, but if either one of them is false, then this guy is false. So you can say, so what that means is that since they share the same truth table, P implies Q and thing, this is logically, so we use a symbol called logically equivalent, that's the one I'm saying. This is the same as this, right? So this biconditional operator is actually the same as P implies Q being true and Q implies Q being true. That's that if and only if thing. So right, so this is what we call logical equivalence. Alright, logical equivalent. And so you may not, so this is just a symbol that we use to show logically equivalent, and you maybe use 3 bars to distinguish it from the regular equals you see with like numbers and stuff. Right? But it doesn't matter, it's just a symbol. Some mathematicians will still use this symbol instead of this symbol. So don't ever get caught up on the symbols. Now, a good mathematician will always tell you how they're using their symbols. And if they don't tell you, then you just assume kind of the default the meaning of the symbol you understand, and you'll know because as you go through the context, it may not be true or false, and then you'll understand how they're actually using the symbol. So that's that. So let's go and so then let's do 2 simple terms, all right? A tautology. So a tautology is a statement that is always true. A statement that, a propositional statement, so that should be implied, a propositional statement that is always true. Always true. Right? So what this means is that if, for example, if P implies so how do you know if a propositional statement a tautology is a statement that is always true. Conversely, we have something called a contradiction, which is a statement that is always false. Tautology, contradiction, 2 new vocab words, right? Which is a propositional statement. Remember, a propositional statement can also be a compound one. It could be made up of like ones. It could be a complex one, right? Propositional statement that is always false. So, what are some examples? What's an example of a contradiction? What's an example of a propositional statement that is always false? Sure. Say you have a proposition P. So the statement P and not P. So try to do the truth table for that, right? So P, I'll do a not P, right? So this is true. This is going to be false. If this is false, this is going to be true, right? And then now, P, and I'm going to do an AND of that, right? Not P. Okay, you should pause and try it for yourself. Well, you know the AND operator. If any one of these is false, then this thing's going to be false, false. So you see that? This statement's always false. This P and not P, so this is what we call, this is a contradiction, which makes sense. A statement and its opposite cannot be true at the same time. Remember that definition in the beginning? Propositional sentence is a declarative sentence that is either true or false, but not both, right? So you can't, so a statement and itself cannot be both. One of the, if a statement is true, then its opposite has to be false. If a statement is false, then its opposite has to be true. It can't both be true and false. It's not like a Schrodinger logic or some weird nonsense like that, right? It's either true or false. That's it. So that's why this is a contradiction. It's always false. Now, on the opposite, what if we had something like P or not P, right? So let's try that one. P, not P, true, then it's going to be false, false, then it's going to be true, right? Now let's do P or not P, right? So now only one of them has to be true. So this is going to be true, and this is going to be true. So this statement is always true. This statement is always true. This one's a contradiction, right? Contradiction. This one's a tautology. Tautology. So it's always true, because what will happen is, if you have a statement P, it's either going to be true or false, right? So whatever value, if it's true, then its opposite is going to be false. But if it's false, then its opposite is going to be true. And since the inclusive or the or, we just call it or. When we say or, it's always implied it's inclusive or. Since this or operator only requires one of them to be true, that's always going to be the case, right? Either something's going to be true or its opposite is going to be true. That's how, if it's a propositional thing, it's going to take on one or two values, and its opposite is going to be the opposite value. So it's always going to be true. So right, so this is a contradiction, tautology. Cool. Alright, and then There's this definition called logically equivalent. That's that, like, logically equivalent. Logically equivalent. So I talked about things being the two statements are logically equivalent if they're two, like, operators are logically equivalent, and if the truth tables are the same. Well, we can be more definitive. Now we know how to be called biconditional. So if if this pi b biconditional q, this biconditional operator, if this statement right here is a tautology, then this statement P is logically equivalent to Q. It means they have the same truth tables. Right? If this P, so what does that mean? Well, we can actually see what this means. So let's say P implies Q. So actually we can let's go back to the truth table, right? That means they have the same truth value. That means these two have the same truth value. So let's see if this is true. We want to prove this, right? Well, you go to the P implies Q truth table right here, right? And now we look at the cases where they're true, those two cases. In these cases they're true. It is, you notice that the P has the same truth value as the Q in both of these cases. You see that? So that means the P was logically equivalent to the Q. They have the same truth value. So that kind of, you should always play around with these when people give you definitions, make sure they match up like that, right? So, that's cool. So one way to show that two statements are logically equivalent is to show that this biconditional implication is always true. How do you show it's always true? Is you show that for all values that P and Q can take on, this will always be true. And we kind of saw that here. Yeah, alright, so let's go. Okay. Yeah, so one final thing in logic before I promise, I know we've kind of overkill this logic thing. So this will be we'll do this as like the last thing in our logic section, and after this we'll actually move on to what we call predicates and quantifiers, and then we can actually get to proofs. Okay, sure. So let's do that. So De Morgan's laws. Okay. So we're gonna, there's this thing, there's this guy, math guy, whose last name is De Morgan. Wanted to be V Morgan, I guess. But anyway, De Morgan's laws. I'm gonna write down the laws here, but I want you to actually think about what they mean. So what De Morgan's law says is that this statement, the knot of the entire statement P and Q, the knot of P and Q, is actually the logically equivalent, means has the same truth table as knot P. Ooh, my battery's running off. Give me a sec, let me just... Okay. Okay. Is the same as not P or not Q. Right? And then it's also saying the knot of an OR statement. So it's saying the knot of an AND statement is the same as knotting the individual guys and then changing the AND to an OR. And it's saying the knot of a OR statement, P or Q, is the same as knotting the individual people, knotting the individual statements or whatever, and then turning the OR into an AND. That's what De Morgan. So now this is actually, today you want to prove this is true. How do you prove this is true? Well, you want to show that they have the same truth tables. That's all that means. This logical equivalence means they have the same truth table. So go ahead, pause and prove that it's true. So you just write the truth tables for these guys. Alright, so you should do P, Q, and then true, 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 false. And if you want to know more, there's these classes called discrete mathematics, which I highly recommend. In fact, it's probably one of the most important. I would say that in the whole field of mathematics, discrete mathematics, basic probability, and linear algebra are probably the three most important mathematical topics in all of mathematics in terms of like for any arbitrary or generic major. Like if you're to pick a major out of a hat, these three mathematical tools are the most important. In fact, It's ironic that we teach calculus even though these are far more important, and only a small subset of you will actually end up using, like, say, direct calculus, like if you work in physics or something. But these concepts, which are not required classes, are actually far more fundamental, and you'll see them on a daily basis and not even realize it, actually, because it's logic, and logic's everywhere. So yeah, so I recommend you take such a class. P, Q, so you should do P or Q. Do the not P or Q. So just save up on time and reduce this lecture time. I won't do this here, but you should do these and show that and see that you'll get the same truth values for the above statements. And yeah, so I'll leave this as an exercise to the reader. Okay. So yeah, you should fill all these guys out, right, yourself, and then yeah, and then you'll basically have proven this. In fact, you're kind of doing your first proof by showing these laws hold by filling out these values. So you should pause and then just do them. Not P and not Q, not P, not Q, right? All right. So yeah. And so actually you can then show a lot of things, like there's a lot of different properties you can show. I won't go into them, I'll put them on the doc, but there's things like something and a true. When you take any arbitrary propositional statement and you end it with a true, you'll always get back the propositional statement. Let's do that one really quick. True, false, then now we have something that's always going to be true. This true guy is a special guy that's a constant. He always says true. Well then, now when you do P and true, when you AND them, this guy's going to be true, this guy's going to be false. You see how these two are the same? What that means is that this AND, P and true, you take a statement and you conjunct it with the true statement, you just get back that statement itself. So this is actually used in a lot of like bit logic. So now, we use this true and false. There's actually in computers you have bits, right? That's 0 or 1. They have the same kind of and or not, right? You can and if they're both 1. The 1 is like a true, and the 0 is like a false. So your computers are literally making decisions based on this, like your bits and everything. It's just true-false logic. So anyway, kind of a side thing, but later maybe I'll do a video on computers and stuff. And so you can see why understanding this is a basic basis of understanding really like how computers work and like what programming is and things like that. So in the same sense, if you do an OR with a false statement, you will also get back the statement itself. So these are what we call identity laws, right? These are like, so you can confirm this yourself. You know, it's a P and a false. So this false guy is a constant. He always takes on false. P is true and false. And then, you know what, do the OR. Only one of them has to be true. It's true and it's false. You see they have the same value, which means they're logically equivalent. That's what that means. Alright, you can do, there's a ton of these laws. These are called like identity laws. And there's things called like domination laws. So you should actually just try as an exercise. I'll just write down the relationships. You should draw the truth tables and see them for yourself. If you don't do that, you won't see these later. And so it's really good to practice these things, because on exams and stuff, when you have them in class, you'll be a lot quicker at these, and exams are timed, so the only way to really get these down fast enough and to be able to be both fast and accurate on an exam is to actually practice these yourself. So do these truth tables, see these things. And eventually, you won't even have to keep drawing the truth tables. You'll just understand them, like, conceptually what they mean. Always when you do truth, ask yourself conceptually what it means. Try, like, the sentences you saw. I would give you those example sentences and things like that. You can always play with that. You can't play with that during the exam because it'll waste your time, right? That's why it's always important what we call front load your learning. What that means is learn as much as you can before the exam, right? It seems obvious, but sometimes we don't do that for various reasons. Maybe we don't schedule enough time. But remember, you're really only in college once, so you might as well make the most of it, right? And you're paying money for, well, a lot of us are paying money for college as well, so it makes sense to, you know, put in that time and effort to just practice, make sure you really understand the stuff well once. You probably won't be taking that class again. Alright, sorry, I didn't mean to get all preachy there. These are called the idempotent laws, right? So if you OR something with itself, then you get the thing itself. If you AND something with itself, you get the thing itself. Okay, you can do that. And then, and this is, oh, this isn't really close. So this is like when you negate the negation, you get back the original. You get back the original statement, right? When you not on a not, the knots cancel out basically, right? So that's kind of cool. So you get the statement back itself, and then the commutative laws. Oh, okay, so you may have heard of that word, commutative, like. So, like, if you heard it in like your introductory math classes back in the day, it means like the off. So I know this sounds really abstract. You're like, oh, how do I ever apply these? Well, once we talk about math, all this will be implicit in your head. These won't come out directly, but by making sure you understand, this is this foundation of logic. I can start talking math basically in the later section, in the later videos and stuff. And even when I talk about application, and you will understand that intrinsically. So yeah, this cute. All right. And so there's a lot of these. I won't go through all of these. I'll put them in the doc. But as you can see, you should try these exercises, prove them. Right, and yeah, and so as you can see though, this shows you that you can do a lot of like, this is why they call it Boolean algebra, right? Algebra is like you have these operators and you have variables, and how do they, and what are, and then you have these equivalence rules, right? And then like how can you, well, you don't have to, but and like, I mean, like, how can you like rearrange this? How can you? It's basically when you think about doing math or doing algebra, you're like manipulating symbols. What are valid, correct ways of manipulating the symbol based on the rules that these symbols represent and definitions, right? That's what, you can think of that as being an algebra, right? In the most abstract sense, Q or R, things like that. Yeah, blah blah blah. Okay. So this shows that I can like move the parent. I can group them differently, and then this overall compound statement with this is the same as this overall compound statement. Yeah. Okay. So that's that. One last thing before I end this video is what we call quantifiers. Yeah, quantifiers. Okay. Predicates and quantifiers. And once we have this, we can basically start math. We can start having numbers and stuff like that. So let's go over something called a predicate. Okay? Alright, a predicate. Predicate is what we call a what's the proper definition? Oops. Predicate. I think the best way, okay, I kind of have to use the word function here. So, but later I will give you a proper definition for function when we go over sets and I think in the next video. So predicate is a yes. Okay, a predicate can be thought of as a statement that is neither true or false. Neither true or false until the values of its variables until the values of its, so it's not a, because remember, this is not a propositional statement. This is just a general. This is just a statement, right? This is important. Until the values of its variables are defined. So what does that mean? So examples, right? So a predicate is a statement that is neither false or true until the values of its variables are defined. Okay, examples are like x is greater than 3, right? So this is the greater than operator, if you remember that. So we find it. Or x equals y plus 3. Remember these things are all not propositional statements, like x equals y plus 3 or x plus y equals z. These are all not because we don't know whether their values are true or false until these are. So these actually have worth. These are like what we call predicates. Okay? So these are called predicates. So if I said something like let x equals 2, then now this becomes a propositional sentence, right? Because now you put in the 2 for the x, you get 2 greater than 3. That's actually false, but it's still a propositional sentence. So now 2 is greater than 3. That's a fact statement. It's a false fact in that case. But this one here is still not, because I didn't give y a value. Or in this case, I have to give both y and z a value. So if I said x, y equals 1, z equals 4, or something, then you can actually, now these are all propositional statements, because they now have values, right? So now we can actually start defining what things that we call like propositional functions, right? Like a propositional function, and later I'll define exactly what a function is, because I need to kind of tell you what a set is, and we need to get a notion of that in there. Then I can actually give you the formal definition of a function. But now just think of your function back to your, like, when you have f of x equals x squared and all those kind of days, right? Like, they would just tell you, they didn't give you a formal set definition of a function, but, you know, so you can think about it, f p of x, so you always just kind of filled in the value. Like, you think of a function, you just kind of filled in the value. I'll give you a proper definition in the next video, I promise. So we can just say, like, p of x equals x is greater than 3, which is also the same thing as x is greater than 3, right? So greater than 3. So predicates take a true or false value, right? Once the variables are defined. So if I said p of 4, that is true, right? That'll be 4 is greater than 3. So I'm using 1 equals here, right? So you can see how you could use like 3 equals logically even, but it doesn't matter. So this is one example of how I might not use the same like notation, but it's the same thing. So 4 is greater than 3, than 3, which is also this true, is true, right? Okay. P of 3 on the other hand is false, because 3 is not greater than 3, it's equal to it. So right, so like as you can see, yeah, so these are what we call propositional functions, right? So these are what we call propositional functions. This p of x is a propositional function. Propositional function. Just like a function that you saw with numbers, except instead of numbers, it's taking in propositional variables. So it's argument. So the things that you give to a function are called argument, right? And so the argument to the function are the things that the function takes as input. So you can think of a function as kind of like a machine, right? P is like a machine. It takes in like these inputs. In this case, it takes in that, and then it spits out something, right? Like, so a function, what it does is that it just takes in something and spits out something. So what a function can take in, so we won't get into this now, but what the set of things, all the things that the function can take in, that is defined to take in, that we call that its domain. And all the kinds of things that the function can spit out for the things that it takes in, that's called its range. And then we have different words like pre-image, image, and all this crap. But like we'll get into those later once we understand sets, since we define sets, okay? But yeah, so you can think of that's what a function basically is. So p of 3, takes in 3, spits out 1. Okay, great. So a propositional function is it takes in all these propositional variables, these true, false things, right? It can take in more than one. It could be a propositional x. You could have another statement, right? Like x is greater than y, for example. So let's take in 2 of them. It can take in any number, right? This is a 2-argument one. That's a 1-argument propositional. That was the one I just erased, was a 2-argument one. So you can do, I'll just leave it back there. So you can have, if they can take in it, but then at the end of the day, the output should always also be a propositional variable. That's the important thing. So its input and its output, like domain and range, are actually the same. Okay. Let's go to, alright, propositional, so that means preconditions. Yes. So the valid inputs to a function are what we call preconditions. In programming, you'll see a word like precondition, right? That's the valid input to a function. So that means, for example, if we have a function that, given a number, it computes its square root, then if that number is like negative, that's the better example. If you have a function that does 1 over x, for example, right? 1 over x, you know that you can't have 0 in the denominator. We'll go over why, but it's basically a definition, and it's important. But like basically, so f of 0 is undefined, right? So the precondition to this function, the precondition of this function will usually be f of x equals 1 of x x not equal to 0, right? So this function is defined as long as we're not talking about x equals 0. That's what we call a precondition. Okay? And then the post condition is basically like rules that the output will satisfy. So what comes out of the function, if it satisfies, those are called post condition. So let's not worry about those. Those are like programming things, but this is an example for some of you may have been studying computer science. So the final thing I want to go over are quantifiers, okay? Alright, so quantification. Alright. So quantification is basically, remember how I told you how that proposition state, like that function, like it doesn't take on, it doesn't become a proposition with a certain truth value until you assign values to it, right? So that's what quantification is to create a proposition. A quantification means to create a proposition from a propositional function. Create a proposition from a propositional function. So we will do some really cool math stuff in the next videos and stuff once we get this and then sets. Yeah, in the next video we'll do some really cool math stuff. This was kind of boring because it's logic, but it's also really important to make sure you understand this. That's why this should always kind of be like a first thing in any class, really, to make sure you understand logic. Otherwise, there's no point in teaching you math if you don't understand logic, right? In fact, there's no point in teaching you almost anything if you don't understand logic, right? History, everything is all based off of some kind of logic when you think about it. But, okay, anyway, quantification, create a proposition from a propositional function, right? So there are two, so many math statements assert that a property is true so there are two kinds of quantifiers. So a lot of times you'll say something like you'll say things like for all, you'll see in math things like for all or there exists, right? So let's go over what these mean. So for all something, so this is like for all numbers x, you'll say something like for all integers, if the integer is divisible by 2, that means you can divide by 2 and not get a remainder, then that number is an even number or something like that, right? So that's like a for all statement. Or you can say something is there exists a number that is not, positive or negative. In that case, that's 0. We've actually defined. So by a definition of positive or negative, 0 doesn't fit either one. So 0 is actually non-negative and non-positive, right? There exists. So there exists means there's at least one. That's an important thing to remember. When you hear the word there exists, it means there's at least one thing that will make the statement true. For all means everything. Every input will be true. Every input to the function is true. Function is true. Okay, so let's actually go over that. So for all, the symbol for that is is a upside down A. It's kind of weird. And there exists. The symbol for the there exists is this backwards E. So I'm thinking, they're probably just running out of variables, so they came up. It makes them. So when I say for all x p of x, what I'm saying is that for every x, the statement p of x. So now you're assigning the x takes on a value, and you're assigning it to the p of x, and then p of x is now going to be either true or false because it has an assigned variable, right? So p of x but this is saying that for all values of x, p of x is true. So a lot of the time you'll say, well, what is x? So when we get into the notion of a set, if S is a set is just, you can think of a set as nothing more, it's really just a collection of objects like cat, dog, or it could be like numbers, right? So and it could be a number, it could be the numbers like 0, 1, 2, and this could be, and it can be finite or infinite, right? So the numbers like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to infinity, that could be a set. And I call that n or something, okay? So what we're saying, so a lot of the times you really will see something like for x element, so you would say for all x in S, p of x. So what that means is that you take each element in the set, you just plug it in, and this thing is true. That's what this is saying. For all x, p of x. Alright? So then there exists means that there's at least one thing that in this set of things, for example, there's at least one thing that'll be true. So I'll go over this for all and there exists in the beginning of the video as I tell you what a set is, and we'll go over what a function is. And yeah, so let's actually call it quits here. And yeah, so this is called a universal quantification. Universal quantification. And the backwards E thing is called a existential. Because there exists existential. There's at least one existential quantification. And yeah, so we'll wrap this up in the next video with when I go over sets and functions, like what that means, what a set is, what a function is, and we'll go back through these. Alright, we'll go back through these, and then we'll actually start some real math, which will be kind of cool. Okay. Thanks for listening. I realize this video might be rough around the edges, please, but then, give critical comments. Say like, oh, this is boring, or you went too slow, or whatever, and yeah, I will try to respond to those. Thank you very much. And to give you an idea of what software I'm using, I'm actually using Open Broadcaster, OneNote on my Surface Pro 3, so let's stop recording.